Chapter 2, The Chemistry of Life, Part 2. In Part 1, we looked at a periodic table, and we read the different information in that periodic table. We also looked at this square that would be found in the periodic table, and we see here that we have the atomic number 11. In some periodic tables, the atomic number would be in the top left-hand corner. The atomic number is going to be equal to the number of protons that are found in the nucleus of the atom. We also have the element symbol, capital N, little a, for sodium, and the element's name, and then the average atomic mass for that element, sodium. So if we round this off, this would be 23. Now, looking at the number of protons, if it's a neutral atom, no charge, then we're going to have the same number of negative charges as we do positive charges. Remember, protons are positively charged, and they're found in the nucleus of the atom. Electrons are found in orbit around the nucleus. And so, since our atom is neutral here, we would have in the first energy level, first orbit of electrons, it's full after 2 electrons, and then the remaining electrons would move up a level, an energy level, and the second level is full after 8 electrons. And then we have 1 left over, so that last energy level is called the valence shell, and it has a valence electron. That valence electron determines the reactivity of that element, and we mentioned that sodium is very volatile, will explode if exposed to air. And it also determines that valence electron also determines the reactivity and how it bonds with other atoms to form compounds or molecules. We can subtract the atomic number from the atomic mass, because remember, the atomic mass is the number of protons plus the number of neutrons. So we can calculate the number of neutrons if we subtract the number of protons, or the atomic number, from the atomic mass. Now, we were talking about the element sodium. Elements are unique substances that cannot be broken down into simpler substances by normal means. There are 92 naturally occurring elements that we know of. We saw the periodic table, and that gives you the information about those atoms of the particular element. And some that are very important to us are carbon, hydrogen, oxygen, and nitrogen, and sometimes we have phosphorus and sulfur. And carbon, hydrogen, oxygen, nitrogen make up about 95 to 96% of the mass of the human body. Phosphorus and sulfur brings it up to about 98, and the rest are considered trace elements. Now, trace elements are required by the body in very small amounts. That's why if a child chews those chewable vitamins and gets into those chewable vitamins and thinks it's candy and chews several of them, they're getting a lot more of those elements than they need, and it becomes poisonous if you take in too much. So trace elements are needed by the body, but they're needed only in very small amounts. And then you have ultra trace elements required by the body in minuscule amounts, extremely small amounts, and too much of a good thing is poisonous. So ultra trace elements are usually poisonous in high quantities, such as arsenic. You know, arsenic is poisonous, but we need a trace amount of that. But if you get more than the ultra trace amount, it is definitely poisonous to us. So these make up about 98% total of our body mass, and then the trace elements and the ultra trace elements make up the other 2%. Isotopes. Isotopes are atoms with the same atomic numbers but with different atomic weights or mass. The atoms with the same number of protons and electrons but different number of neutrons. Remember, the number of protons is the atomic number of an atom, and that is not going to change. If you change the number of protons, you're also changing the atomic number. It will not be the same element, not the same atom. So this doesn't, under normal circumstances, change. So the same number of protons and electrons in a neutral atom, but a different number of neutrons. So if you have a different number of neutrons, the atomic weight is going to change. Remember, atomic weight is the number of protons plus number of neutrons. Oxygen often forms isotopes like O16, O17, O18, and that number is expressed as a superscript. So again, you have the same number of protons but different number of neutrons. Unstable isotopes are radioactive. They emit subatomic particles like uranium, plutonium, those radioactive elements. Over thousands of years, those radioactive elements could decay enough to become a different element, but under a different type of atom. But under normal circumstances, this doesn't happen. You would have to have extreme energy, fission or fusion, for that to happen. So if you have the atom of an isotope of a particular element varies in the number of what? An isotope varies in the number of neutrons in the nucleus of that atom. Molecules and compounds. Molecules are particles formed when two or more atoms chemically combine. A compound is a particle formed when two or more atoms chemically combine, but they're from different elements. So a compound is a particle formed when two or more atoms of different elements chemically combine. Now look at this statement that I have here. I want you to determine whether or not it's true or false. All compounds are molecules, but not all molecules are compounds. Well, I'm going to go ahead and advance the next bullet here, and we can look at these chemical formulas, also called molecular formulas, of different compounds. Now, molecule is a particle formed when you have two or more atoms chemically combine. A compound, two or more atoms of different elements chemically combined. All compounds are molecules, but not all molecules are compounds. Okay, so a compound has to have elements from different, or atoms from different elements. Okay, let's look at hydrogen right here. Now this subscript in this chemical or molecular formula tells us that there are two atoms of hydrogen bonded together. And we talked about hydrogen before. If we had just one atom of hydrogen floating around in our atmosphere and a whole bunch of those, then our atmosphere would blow up. It's very volatile because it has one proton in its nucleus, 1 electron in its outer shell, its valence shell, so it makes it very, very volatile. So in nature it will always be, in our atmosphere, it will always be combined with another hydrogen as H2, so 2 hydrogen. So let's look at these definitions. Is that this chemical formula or molecular formula of H2, is it a molecule? Particle form when 2 or more atoms chemically combine? Yes, this is a molecule of hydrogen. Is it a compound? It's a particle formed when 2 or more atoms of different elements chemically combined. There are no other elements besides hydrogen here, so this is not a compound. Now let's look at this one. We have 6 carbons, 12 hydrogens, and 6 oxygens. So it is a molecule because it's 2 or more atoms chemically combined, and it has carbon, hydrogen, oxygen from different elements that are chemically combined. It is a compound. So all compounds are molecules, yes, but not all molecules. This molecule is not a compound. So this statement is true. Now, we have the number of atoms depicted in this, or represented in this molecule. And by the way, you can look at the ratio between the carbons and the oxygen and hydrogen, and it's 2 to 1. And that tells us, usually 2 to 1 means that this is going to be a carbohydrate. This is glucose. You are probably familiar with H2O, 2 hydrogens to 1 oxygen. By the way, there is no subscript here, but because we have the element symbol here, it is understood that this is 1 oxygen. This is H2O, or water. By the way, if we had a 2 right here, H2O2 is hydrogen peroxide. So just as a review, before we start talking about the bonding of atoms, the bonds form when atoms combine with other atoms. Electrons of the atom occupy regions called the electron shells, or energy shells, or energy levels, which circle the nucleus. And as we stated before, for the first 18 elements on the periodic tables, the first 18 atomic numbers, the following rules apply. We know that the first shell is full after it has 2 electrons in it. And then the remaining electrons will move to the second shell, and it can hold up to 8 electrons. And the third energy level can hold up to 8 electrons. This only works for the first 18 elements. And the elements that go above 18, it's somewhat predictable in the energy levels of their electrons, but it's not always the case. Ions. An ion is an atom that has gained or lost electrons. It is an electrically charged atom. The atoms will form ions to become stable. A cation, notice my little green T here so you can see it's like a plus sign. A cation is a positively charged ion. It happens when an atom loses an electron. An anion is a negatively charged ion. It's formed when the atom gains an electron. Now remember that in the nucleus of the atom we have protons, and protons are positively charged. In a neutral atom, you'll have the same number of electrons in orbit around this nucleus, the same number of electrons as you do protons. And we've looked at sodium before. That first energy level has 2, and so it's full, and then the next energy level has 8, so it's full. 2 plus 8 is 10. We had 1 more electron. Sodium, very volatile. So in order for it to become stable, it will tend to give up that electron, and when it loses that electron, that sodium becomes stable, and now it has 1 less negative charge than it has positive charge. So it has 10 electrons and 11 protons. Therefore, that sodium will become an ion, or positively charged. Now, chlorine can receive that electron. Now, let's look at chlorine for just a minute. Here's the nucleus of the atom. It contains, for chlorine, its atomic number is 17. And so it has 17 protons in its nucleus, or 17 positive charges. Now, it would, in a neutral atom, it would have 17 electrons. So 2 in the first energy level, 8 in the next energy level, and 7 in its valence shell. Okay, so it's missing 1, so it's somewhat volatile too. You know, it's dangerous to work with chlorine at a swimming pool. You have to be very careful, or you burn up your lungs with it. Okay, it's pretty volatile. And what happens is it will receive an electron from another atom. In this case, sodium gave up its 1 electron, so it bonds pretty easily with and forms an ionic bond between this sodium and this chloride. But the sodium gives up. If we were to split that molecule of sodium chloride, this would be stable because it gave up its electron, and then the chlorine would become chloride, and it's become stable because it gained the electron. So the sodium will tend to give up the electron, and chlorine will gladly take it. So after it takes that electron, it has a full outer shell. But to have a full outer shell, now it has 18 electrons, but only 17 protons. So it has 1 more negative charge to the positive charges. So the chlorine becomes an anion. The sodium a cation, and the chlorine an anion. And after it gives up its electron, that's called oxidation. Oxidation is when electrons are donated to another atom or lost, and this molecule or this atom will become oxidized. Okay, now the chlorine is receiving this electron, and we call that reduction. The molecule gains an electron and becomes reduced. Okay, so this is called the oxy-redox reaction because you have oxidation, giving it up, and then gaining an electron is reduction. Redox reaction is what this is called. And next time we'll look at ionic bonds and polar bonds and different types of chemical bonds in part 3.